Hello everybody, and welcome back to another CIV 398 assignment guide. So in this assignment 4, it's actually a nice, short, simple assignment, 4 questions instead of the regular 5, and it has to do with strains. So we're going to mainly deal with strains, and then at the end we're going to sprinkle a little stress on, but as you guys will see, it's not too bad. There's one question that's a little bit long, but overall the assignment's not too bad. I tried to make it a little bit nicer because I know you guys had a midterm this week, so hopefully you guys found it a little bit nicer. So we're going to start with question 1, and question 1 is easily the easiest question of them all. So what question 1 says is a rod with a unit length. So a unit length means that the current length, undeformed length, is equal to 1. And it's subjected to uniaxial tension. So let's say that we have a bar, we have this nice bar of steel, and we're just pulling it in one direction. Let's say we're pulling it horizontally. And it says, determine the instantaneous length, so the deformed length of the rod, under the following conditions. And the first three, A, B, and C, are when we give you 3 values of strain. So as we can see, the values of the strain are the exact same. In my randomized question, I got 0.078. But the only difference is these are different strain measures. So if we look at part A, we're talking about the engineering strain. We look at part B, we're talking about the true strain. And then finally in part C, we're going to talk about the green strain. So as we can see, all the strains are equal, but they're different types of strain measures. So we're going to determine, okay, well, what does the instantaneous length of the rod look like under these different strain measures? Part D says comment on the difference in the instantaneous length in the 3 scenarios above. So as you guys will see, A, B, and C will give you different lengths. It's going to be obvious. A, B, and C will give you different lengths, and all you guys are going to have to do is look at them and say, okay, well, let's say the engineering strain gives us a smaller length than the green strain, something like that, so that's not going to be bad. And in part E says, is there a stretch ratio? And I don't know why it says stretch ratio on. That's obviously a big mistake. Where the engineering strain, the true strain, and the green strain are all the exact same. And I'll kind of spoil it now. Yes, there is, and we'll discuss that a little bit in the next slide. So I only have one slide for this question because it's that easy. So if we look at the formulas for each strain measure, engineering strain can simply be found by going lambda minus 1. The true strain is just simply the natural logarithm of lambda. And finally, the green strain is 1/2 lambda squared minus 1. And you guys just say, okay, well, I know these strains. I know the engineering strain, I know the true strain, and I know the green strain. So with this, I can figure out what lambda is in each one of these equations. And as we see, lambda is the stretch ratio. And you're saying, well, Clayton, the question's not asking me for the stretch ratio. It's asking me for the instantaneous length, not the stretch ratio. Well, we know that this stretch ratio is actually very closely related to the instantaneous length. So if we look at the formula for lambda here, that L, that's the instantaneous length, L naught, that's the undeformed length. And we know that it's actually a unit length. So in this particular scenario, and I'm going to highlight that again, this particular scenario, lambda, our stretch ratio, is actually equal to our instantaneous length, only because L naught, our undeformed length, is equal to 1. Now, be ready, because in a midterm, Dr. Sammer can easily make that undeformed length, let's say 2, and then things will change. So just kind of be careful. So finding the instantaneous length for these are actually very simple. All we have to do is look at each formula, which are very simple in nature, and we just solve for lambda. That's it, that's all, nice and easy. And then the last part of the question says, is there a stretch ratio in which all the strains are the exact same? And there has to be. And my hint to you guys will be, think of strain measures. They're based upon formulations. And think of the undeformed length. Let's say that I don't apply any strain at all. So the strain is 0. All strain measures should give me the exact same thing. Should. So check it out. Let me know what you guys think. And that concludes this question. Again, like I said, nice and easy. Probably the easiest one of the assignment. I hope this helped. I will see you guys in the more challenging questions, questions 2, 3, and 4. All right, guys. Thanks for listening.